blood pressure should be higher. Your mean arterial pressure in arteries is higher than it is in veins. I've given you these numbers before. I'd be surprised if anybody remembers them. On the capillary side, it's rarely above 30. On the vein side, it's usually around 10 as far as your blood pressure. What I think it was here, 35? Okay, I think it was 35. Okay, so on my artery side, my blood pressure, we'll use the book's example, 35 here. Like I said, that's a little higher than typical. And on the vein side, I think it was 10, 8, I think it was 10. No. They don't give us one because this is on the arteries. Okay, so we'll put 10 in here. Interstitial pressure. That'll vary a little bit. It can go from anywhere from about 5 to -3, anywhere in that range. And I think your book gives you what, 0? Yeah, 0. Hydrostatic pressure. They give you the value of 0. Now wait a minute. I thought I just said that anytime you collect fluid in a space, you have pressure. Did I just say that?
Yeah.
Okay, so did I paint myself in the corner, or is there some magic rabbit I can pull out of the hat to make this make sense? It's got to be a magic rabbit.
Yeah, magic rabbit.
Magic rabbits. Okay. Well, there's a little bit more to this story, and that is that not all of the fluid that goes into the interstitial space goes back into the veins. Some of it goes somewhere else. Anybody know where that mysterious second place might be? About 5% of the fluid is drained away by something else. Your lymphatic system. Okay. You have a second type of circulatory system that parallels your arteries and veins. It's called the lymphatic system. And it basically suctions away some of the interstitial fluid and drags it through a bunch of tapioca-looking little nodules called lymph nodes where it filters it. And it pulls proteins out of that and helps activate your immune system. And the end result of the lymphatic system is to take all of that interstitial fluid, and once it gets back up here to the subclavian veins and the brachiocephalic trunk, it just puts it back into the bloodstream. But from the interstitial space, it pulls it away. When it does that, it lowers the interstitial fluid pressure. Okay? So that interstitial fluid pressure might be up around, like I said, 3 to 5, but with the properly functioning lymphatic system, it drops it. It can even go negative. It can go down to about -3. So the way to remember that is just remember the lymphatic system sucks, okay? And that pretty much sums up that effect, okay? That lowers the interstitial fluid pressure, okay? And that stays pretty constant right around there, unless you have lymphatic blockage from either, say, some kind of lymphoma or some kind of parasitic worm infection where it's blocking the lymph nodes, then that pressure can become very positive and can cause some problems. Okay. Got our 4 pressures outlined? Know what they are?
Yeah.
All right, so there's an essay question on the test that deals with this, right? And so you're going to have to start off by explaining what the 4 pressures are. And then we just sum them up, okay? Now there are 2 forward pressures and 2 rearward pressures. 2 forward pressures and 2 rearward pressures. So a forward pressure is something that's pushing us out of the artery into the interstitial space. That's a forward pressure. Okay. Pushing us out of the arteries or out of the vessels, pushing us out of the vessel and into the interstitial space. Blood pressure. Is it a forward pressure or a rearward pressure? Rearward pressure is drawing it back into the vessel. So what do you think? How would you describe blood pressure? Forward or rearward?
Forward.
Forward. Okay, yeah. Blood pressure is definitely that's the main forward pressure. So we'll put forward. Okay. Interstitial fluid pressure. Is that drawing fluid into the interstitial space or trying to push it out? It's trying to push it out. Now right now it's 0, so we can, it's something that's negligible because it's 0. But ordinarily the fluid pressure, the interstitial fluid pressure, if that number were positive, that'd be trying to push the fluid out of the interstitial space back into the vessels. Okay. So that's a rearward pressure. Colloid pressures. Blood colloid pressure. Forward or rearward? Rearward, right. Blood colloid osmotic pressure is the main rearward pressure. That's what's drawing fluid back into the vessel. So we'll put a big R next to this guy. That's the main rearward pressure. Well, okay, by process of elimination then, interstitial colloid osmotic pressure had better be a forward pressure. That's trying to suck fluid into the interstitial space. Okay. Now, whether fluid goes out of the vessel or into the vessel is determined by the sum of these four. Okay. And we call that net filtration pressure. NFP, net filtration pressure. Okay. And you can sum up net filtration pressure two different ways, and I'll show you both ways. Okay. One, the way they do it, they take the two forward pressures and add them up. These are our two forward pressures. And they subtract from that our two rearward pressures. That's how you remember that. Okay. You can try to memorize it, and frankly, I'm terrible at memorizing things like that, so I just remember the two forward minus the two rearward. So let's do that. Let's go and run through that exercise. Well, they do it right here. Okay. Hydrostatic pressure in the capillary is 35 on the artery side. Right, that's important. That's on the artery side. Osmotic pressure in the interstitial fluid, that doesn't really change. That stays at 1. So we sum that up, and that's 36. Okay. And we subtract away from that. Well, our hydrostatic pressure, the interstitium is low. That's a 0, so we can ignore that. So the osmotic pressure of the capillaries, that's fairly high. That's 26. So our NFP on the artery side is just 36 minus 26, so there, that gives us our 10. Okay. NFP is 10. So this all boils down to, on the artery side, NFP must be positive. Okay. On the artery side, NFP must be positive in order for fluid to flow out of the arteries. Okay. Now we'll change some of these parameters and see what happens to that number. What do you think? If you increase NFP, will bulk flow increase? If you increase NFP on the artery side, well, let me be very precise about my phrase. If I increase NFP on the artery side, will bulk flow out of the arteries increase? Yeah, right. Okay, what do you suppose the number one factor that might do that would be? Look at the pressures that are up there. Which one could your body really easily change? If I all of a sudden wanted to bathe my pancreatic cells with more interstitial fluid, how can my body achieve that?
You know, I was just thinking about that this morning.
Were you?
Yeah, I really was.
You know, sometimes I have trouble sleeping at night.
Yeah.
It's that, and where was that last cat video I watched?
Right.
Those are the two things that really are on my mind most of the
How
time.
did you read my mind?
Well, look at what are the two pressures that we really have to look at? There's only two that.
Yeah, the
Right.
hydrostatic pressure
Yeah, you've got hydrostatic pressure and colloid pressure.
and the colloid.
All right. Well, colloid pressure is dependent on the blood proteins.
Mm-hmm.
That's probably not going to be super easy to change. Okay.
Fluid intake.
But blood pressure is easy to change. Okay. Even easier than than fluid intake. Just increase cardiac output. Just make the heartbeat harder.
Okay.
That drives your blood pressure up, and that's certainly going to increase your BCOP. I'm sorry, not BCOP. Your blood hydrostatic pressure.
Mm-hmm.
Your blood pressure is going to go up, and that's going to increase perfusion. Yeah, that's the simple thing to fix. Okay. If I need to perfuse my organs more, I just drive up blood pressure. Now those myogenic mechanisms can kick in, and the organs that don't need more bulk flow, they constrict a little bit, so we don't let the pressure go up. And the ones that do need more flow, well, they go ahead and dilate, and that pressure will go up, and we'll get more bulk flow going out. We'll perfuse those organs, and your spleen will swell up, and your liver will swell up because we're getting more fluid flow through them. Okay, or your skin will blush. Okay, and you'll get more blood flow through the superficial capillaries. Okay, so then all we got to do is get that fluid back. 95% of that fluid's got to come back into the veins on the other side. This is a little problematic because the blood pressure in the veins is much lower. Okay. So now we go to the vein example. NFP is still going to be in the driver's seat. Okay, but on the vein side capillaries, NFP must be negative. NFP must be negative on the veins, on the vein side capillaries. A negative NFP means we're drawing the fluid back into the vessels. So in the venous side capillaries, NFP's got to be negative. Now over here on the board, what I tell you the main rearward pressure is? Still there. BCOP, right? Colloid pressure. That's like a sponge drawing the fluid back in. So the trick on the vein side capillaries is this. Drop the blood pressure low enough in the vein so that it is lower than BCOP. As long as blood pressure is lower than BCOP, BCOP, the colloid pressure will draw the fluid back in. And so that's what we do. If you look over here at NFP, some of the things don't change. The interstitial fluid pressure, that doesn't change. Okay? The hydrostatic pressure doesn't change. So really, we don't have to worry about those two. But what does change? Well, look at the blood pressure. The blood pressure on the veins here, they're giving you a fairly high vein blood pressure at 17. That's probably closer to 10 usually. Okay. So this pressure is much lower. Remember in the other example it was 35 on the artery side. Okay, so it's a lot lower. BCOP doesn't change. The colloid pressure doesn't change. So now my rearward pressures are higher than my forward pressures. Giving me an NFP of negative. Okay. And that'll ensure that fluid comes back into the veins. So in this essay, I need to be able to see that to tell me what the four pressures are and just loosely describe them. Okay. It's fine to tell me that capillary hydrostatic pressure is blood pressure. Fine. Okay. Interstitial fluid hydrostatic pressure is just pressure attributed to the collection of fluid in the interstitial space. It's held low by the fact that 5% of the fluid is drawn away by the lymphatic system. Okay, good. You don't need to go on for a paragraph explaining each one, just 1 or 2 sentences. You need to tell me that colloid pressures are due to the proteins dissolved in the fluids. That blood has a lot of protein dissolved in it, and so it has a high BCOP, around 26. Interstitial fluid doesn't have a lot of protein in it, so its colloid pressure is quite low, usually around 1. Okay? And then just for kicks, guys, we'll talk about this in the blood chapter, but it's a good time to introduce it now. The main protein found in your blood is a protein called albumin. The main protein, or group of proteins found in your blood, they're called albumins, and they're liver proteins. So your osmotic pressure in your blood is maintained by 3 major classes of proteins: albumin, globulins, and fibrinogen. Those are the 3 main types of proteins found in your blood. The vast majority of it, like 85% of it, 85% of it is albumin. Okay? And then you have the globulins and 1 to 2% fibrinogen. Okay? Now the money line here is that those are all synthesized in the liver, almost all of them. So liver function is tied to blood colloid osmotic pressure. If your liver function is impaired, osmotic proteins, their synthesis will go down and BCOP will drop. Anybody know anybody that's ever gone through liver function, liver failure? Okay. Right. Well, it's very common. It's one of the more common self-inflicted diseases in society. Well, you could get it by eating toxic mushrooms and things like that, but the most common thing would be alcohol. The overconsumption of alcohol over time causes the liver to become fatty and indurated, and then we call that cirrhosis, and you wind up getting more useless connective tissue in the liver and less functional hepatic tissue. And so liver protein synthesis goes down. And how do these people look? If you've ever seen one, what do they look like when you look at them?
Yellow.
They can look a little yellow, and that's because they're not processing bilirubin correctly. But what about their flesh?
Mushy. I mean, they're skinny.
Well, yeah, they might be skinny, but they're usually puffy. They're puffy.
Because of the black, the edema.
Right. Yeah. They have what's called pitting edema. They have edema. They have too much fluid collecting in their capillary beds, in their interstitial space, because their BCOP is too low. Okay. If you think about that, BCOP is the main rearward pressure. So if you drop that number down to 18, you're barely going to get the fluid to come back. Right? And so it's going to collect in the interstitial spaces, and so you look puffy. That's what happens in that case. Right? In extreme cases of this is what happens in starving people. Okay, I remember being a kid watching. Back then, it was Ethiopia where everybody was starving. It just seems like every couple of years, just wherever the large group of people are starving changes. But when I was a kid, it was Ethiopia. And so you'd see these pictures on TV of these little, just bones, right?